Hello students, welcome to Physics for Everyone classes. This is your Satish sir. In this section, we can see the topic, the gravitational field intensity at a point inside the cavity of a solid sphere. There we can imagine the solid sphere is the Earth itself, or we can use a cricket ball. So there we have got the material of mass m and the radius r. There you can see. Here we have got a solid sphere of mass m and radius r. From this solid sphere, we are removing a smaller mass, which is also in spherical in shape. There you can see this part of mass is removed from here to the outside, and there at this place you will get an empty region. That portion is called as cavity. Now this sphere has a cavity inside it. You see, m is the mass of the sphere before forming the cavity. Be careful with that point. M is the mass of the entire sphere before removing a certain mass from it. Now our target is to find the gravitational field intensity at any general point inside this cavity. There you can see I was choosing a point P here. This is a general point. And to find the field intensity due to the sphere having the cavity, how much it is, its magnitude as well as the direction. This is our target. And this sphere has got its center. It is denoted by O. There you can see this is the center of the sphere, where O dash is the center of the cavity. Nothing is there here. We can call it as the cavity, whose center is how much? O dash. And the separation between these 2 points, there you can see here in this picture, the separation between these two is taken as A. In vector form, we can take it as A bar. And the distance from point O to the point P, where we are chosen, we can take it as R1. There you can see. As this point is a general point, there you can take in the space. It is not lying on the same XY plane. You can see this is a general point. This is the reason we are choosing a position vector from the origin, denoted by how much here it is R1 bar, where R1 bar is the position vector to define this position P from the center of the sphere, from the point O. Similarly, we are taking a reference from the center of the cavity also. How much the distance is R2, or we can call it as the position vector R2 bar. So where R2 bar is the position vector from where? From the center of the cavity, denoted by O dash. So what is A bar? It is the position of O dash with respect to the O. R1 bar is the position vector which defines the point P with respect to the point O. R2 bar is the position vector which defines the point P from the center of cavity O dash. Now this point comes as inside point to this entire sphere. You can see. As you know, how to find the gravitational field intensity for the inside point for the solid sphere, how much the expression is. Here you can see for the inside point, I'm writing the equation E is equal to, so Gm by r square into x divided by r. So this is the field intensity at which point? Inside the solid sphere. On the surface, you can directly write Gm by r square. And outside point also it comes as Gm by small r square. But inside point, take care, the expression comes as Gm by r square into x by r, where x is the position of the particle from the center of the sphere. We have to use this expression to find the field intensity at the point. But here, how to get the net field intensity at this point? Because we are removing some parts from it. To get that one, we are doing the field intensity at the point P, which is equal to the field intensity at this point P due to the entire sphere. What is E1? E1 is the gravitational field intensity at this point due to the entire sphere before removing some mass from it, before forming the cavity, and whose direction is always acting towards the center of the sphere. This is the point, this is the center of the sphere, and we are choosing the point here. The field intensity at this point due to the entire sphere will be acting towards the point O. So here it is. And this comes as this arrow represents this is E1 bar. Here you can see. After removing some mass from it, that forms the cavity. And you want the resultant field intensity at this point. What we should do? We need to subtract or eliminate how much the field intensity which is being produced by the mass which is assumed in this cavity region. And here this point is also the inside point for the assumed mass there inside the cavity. So the field intensity at this point due to the mass, how much we are removing from there, which is acting towards the center of the cavity. There you can see this arrow indicates the field intensity at this point due to the mass which is going to remove from this bigger sphere. So E1 bar minus E2 bar, which will give you the result, the field intensity due to the sphere having the cavity. Now, E1 bar minus E2 bar, we got what is E1 bar and what is E2 bar. We need to find these two expressions with the help of this equation. This is the field intensity at the inside point of the given sphere. Now write down what is E1 bar. We are writing in vector form. So E1 bar with this equation, how much it is? G m divided by r square into x, where x is the position vector. There you can see distance wise, if I am writing, I can write like this. The distance is how much? Simply r1. You can write it here, r1 divided by capital R, divided by capital R. But this is entirely the magnitude. If you multiply this magnitude with the unit vector, you will get the E1 bar in the vector form. So how much is the unit vector along this direction? There you can see r1 cap. Here r1 bar is the vector. If you take r1 cap, it comes as the unit vector along the same direction. So multiply here with r1 cap. So what is r1 cap? Is the unit vector along the direction of r1 bar. But E1 bar is opposite to r1 bar. So we need to place here negative sign. When you take these two, this is the magnitude of the vector with the unit vector, you will get the vector. So R1 into R1 cap comes as R1 bar. So change this one as E1 bar is equal to minus G M divided by R cube. So R square into R cube, and R1 into R cap is how much? It comes as R1 bar. And again, because how much we are removing, how much mass we are removing from the bigger mass capital M, we don't know. So this is the reason we are not expressing in terms of mass. We can change in terms of the density of the given material, because mass is equal to density into volume. So this can be changed as minus G into mass is equal to how much? Density of the sphere into its entire volume, which is equal to 4 by 3rd pi r cube. You can write it as rho into 4 by 3rd pi into r cube into r1 bar divided by r cube. There you can see r cube get cancelled out. And finally you got how much it is? Minus 4 by 3rd pi into G rho into R1 bar. So with this, we can directly write the equation E2 bar also. Because 4 by 3rd pi constant, G rho also constant, only the change is the position vector. So if you know the position vector to this point from the O, how much the distance is R1, we got E1 bar. Similarly, we can find the E2 bar because we know the position vector to this point from the O dash, how much it is R2 bar. So there it comes as, can I write it? It comes as similarly E2 bar, which is the field intensity at this point due to the removed mass. Due to the removed mass. How much it is, which is equal to, with this we can write minus 4 by 3rd pi G rho into how much is the position vector? R2 bar. Because as we know, this field intensity in terms of some general constants, the only one thing is there, this position vector. So I am replacing R1 bar as R2 bar. What you will get? You will get the E2 bar. And to get the resultant field intensity at the point P, we have got the equation here, E1 bar minus E2 bar. Just to keep the values which we got here, let us substitute E1 and E2 in the above equation. So how much you got E1 bar? It is minus 4 by 3rd pi into G rho into R1 bar minus E2 is this one. So 4 by 3rd pi into G rho into how much? R2 bar. Here minus is already there and this also have minus. So minus of minus comes here plus. So E1 bar with negative, E2 bar also we got with negative, but minus is there in the equation and this minus and minus comes as here positive. And from this we can take common 4 by 3rd pi into 0. So what do you get the first term? Minus R1 bar. Second term is plus R2 bar. Or we can say it as R2 bar minus R1. You can see from this triangle O dash and point P, from the triangle of vectors, what we can write? A bar plus R2 bar minus R1 bar is equal to 0. There you can see the first vector is A bar. This is we can call it as the starting point, the end point. We can say it as head and tail. And the second vector starting point is connected to the first vector end point. So we can add these two. And this is the second vector end point. And here it is coming the third vector and point. So what we can take? We need to take the negative vector of this one. So what you will get here? A bar plus R2 bar minus R1 bar is equal to 0. So what do you want here? R2 bar minus R1 bar. With this you will get R2 bar minus R1 bar is equal to minus A bar. So what we are getting here? I am writing here. So R2 bar minus R1 bar is equal to minus A bar. So replace this value with this equation. So 4 by a third pi 0 into R2 bar minus R1 bar. How much? Minus A bar. And finally got the result minus 4 by a third pi 0 into A cap, which is the resultant field intensity at the point P due to this sphere having the cavity. So inside the cavity we got this expression. By looking this expression we can say the field intensity at this point is depending on the separation between the two centers. The one is the center of the sphere, bigger sphere. The second is the center of the cavity part. It is not depending on the position vectors either R1 bar and R2 bar. So wherever you take this point, there inside this cavity, maybe here, or here, anywhere you choose this point arbitrarily as you like. Always you will get the result how much? Independent of the position vectors R1 bar and R2 bar. So with this we can say the field intensity magnitude inside the cavity is constant, and also the direction is unique, which is opposite to the direction of A bar. As you see, the A bar direction, there you can see from here to here is A bar. This is A bar. And this field intensity is negative of A bar, means opposite to the direction of A bar. So inside this cavity, there you are getting, I am replacing here, there you are getting the field intensity is opposite to this A bar. There you can see the lines. All are directed towards, there you can see from right to left. Not saying it is towards the point O. All are not directed towards the point O. They are just opposite to A bar because it is a three-dimensional picture. There you can imagine this is a three-dimensional field. But all the lines are coming from right to left within this region. So we can say it is the field has a constant magnitude and a unique direction. We can call it as a uniform, what you can say, uniform gravitational field, which is formed inside the cavity of the given solid sphere.